Now, so today we're going to look at differential relationship of trig functions. Now, all right, what we're going to look at is in your formula sheet, you'll be given fx equals to f of x sine x and the first derivative of sine x, first derivative of cos x, but not the first derivative of tan x. All right, I will show you that, and it's a requirement in the syllabus to show you how we can derive the first derivative of tan x. All right, if you do specialist, you will be using that a bit more, but you must know as well. So what I'm going to do is use a graphical approach to differentiate the basic sine and cos curves in the form of y equals to a fx plus d, where fx is function sine x or cos x. All right. Then we'll think about differentiating the sine and cosine function by first principle. And this limit, we need to think about the limit of sine h over h and cos h minus 1 divided by h as h approaches to 0. And I will use the derivative of sine x using the geometric construction of the unit circle and tangents, and use the quotient rule to derive ddx of tan x. All right, that you have to. I'll show you, but I'll let you try it first. Now, let's recall. When we look at unit circle, we know that the coordinates xy is actually cos theta sine theta, correct? And if you plot the graph of sine x, you can see that this is a wave and one is lagging, or one is ahead of the other by pi. All right? Yeah? So you can see that that's what happened there. All right? So now what we're going to do is how are we going to derive the first derivative of sine x and cos x. Very quickly, I want you to sketch. If you've got y equals to sine x, y equals to cos x, how are you going to derive the derivative function, the graph of the derivative function of sine x or cos x? Just quickly sketch it. I deliberately did not want to print this for you. I want you to sketch it and think about how you could do it. So if you're not given this as a y equals to sine x, y equals to cos x, and you're just asked to draw the gradient function, what do? Think about the stationary points and the horizontal points of inflection, which is root. And also the oblique point of inflection is maximum or minimum stationary point. All right? Now, if you start off with stationary points, what I do is in this sort of situation, I always draw a straight line down from the stationary point. It makes life a little bit easier for yourself because straight away you can see that this is first derivative. You need to know this, all right? You really need to know this. So you know that here, that is the point that you would, the line will go through, correct?
Yeah.
Yeah? So these are the points. So now I've got 3 points. That's the stationary points. Now think about the oblique point of inflection. So it will be somewhere here, right? So you can see that that is negative, 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 and that point, there will be the highest negative slope, and then there will be a turning point and going up. So the other thing that I would do is just draw the line. Again, draw the line at the oblique point inflection. So you know more or less the graph. So for example, this graph, you know that this bit here, this is positive, this is negative. So it will go down, correct? Positive gradient, negative gradient. So it will go down, right? And then we'll go up this way. This is the stationary point, go up. And then here again, this bit here, you know that there's a maximum there. So you're drawing that up and down. And again, this is a minimum. All right? Same thing will happen to the other one. Here, you know that this bit, it will be negative, correct? And then 0. Yeah?
Yeah.
Yeah? Agree?
Yeah.
Do you agree? So what would happen? Where would it go? If it is negative, it will go that way. Correct? Yeah?
Yeah.
Agree? Do you all agree with me?
Yeah.
But then there is a turning point. So there's a turning point up there. Alright, and then positive and then down. So there's a turning point up there. And
negative sign.
got it? So if you're not given the sine x and cos x, if you don't know, you just look at this function, you should be able to draw the sketch, the gradient function. Do you agree? Yeah? Now, what does this look like? What does this look like?
Cos x.
And what does this look like?
Negative sign.
Negative sine x. Very good. So let's think about how are we going to derive it. Before that, I have to mention, I've got to really emphasize that when we investigate the differential relations of the trigonometric functions, all angle measurements are in radians. All right? So we could use this in many situations. We could use this in terms of the rectilinear motion. It could be the rectilinear motion is defined by y equals to something, y equals to cos x, y equals to cos x plus 1 or whatever. All right? You could think about things as moving up and down in terms of spring, or which is something like tides where there's a cycle, and things like Ferris wheel. All right? Now, please do not write it down because you're going to get this. All right? You will have this when I upload the slide. So if you're differentiating fx equals to sine x by first principle. Now you always know first principle is the limit of h approach 0, f of x plus h minus fx divided by h. Yeah, agree with that? So here, I need to put in a sine x plus h minus sine x over h, because I'm substituting the x with x plus h here. Now, from last year, you should know that sine x plus h is sine x cos x plus cos x sine x, correct? Sine h, sorry, and that take away sine x. Happy with that? So I'm just manipulating. I'm manipulating it, and I am actually, what I'm doing now is think about splitting this. Sine x cos h, take away sine x. All right? Group the sine x together, and then group the cos x and sine h together. So from there, what I can do, I'm looking at the limit of h approach 0. I can actually factorize the sine x out. We have cos h minus 1 over h. All right? We're looking at this h approach 0. All right? Not worried about x, we are worried about h approach 0. Same here. I am factorizing the cos x out because I'm worried about h approaching 0. That's it. All right? Now, we therefore have this cos x, limit of h sine x over h, sine h over h, and take away sine x, limit of 1 minus cos h over h. All right? Now, how do I actually think about establishing the value of this? How do I do that? Now, what I've done here is I'm taking the negative out. So therefore, it became 1 take away cos h. All right? I'm taking the negative out. That became 1 take away cos h. That's the reason for doing that. Now, let's start off by looking at the limit of this. All right? Now, can you get your class back, please? Can you evaluate the limit of sine x over x? Get your class back, please. Anyone without class back? All right, and then use your class back to plot y equals sine x over x. Now, that would be an issue when you plot sine x over x, correct? For what value of x does that not it will not happen? 0. Yep, because x cannot be 0, sine x divided by x will be undefined. So, however, I know for your class back, it will show that point as a continuous point using your class back. Alright? You know that the limit of that equals to 1. And how am I going to prove it? Class back says so, but I still need to prove it. So once I plot that, I use a slightly different program. I didn't use a class back. This one clearly shows that here is undefined for x equals to 0. The function of y equals to sine x over x. It's undefined for x equals to 0. Now, what we really want is, how do we get limit of sine x approach x? How do we find when are we going to approach from the negative end, or are we going to approach from the positive end? Or we can come around and see what is the value. Just approaching this point here. That's the limit. So, I've cheated. I've just took this from the book. So if we look at the table of values, as x approach from the negative side and x approach from the positive side. And if you work out this value, sine x over x, as x approaches 0, what happened? Sine x over x becomes 1. So, what we do now is we have established sine h over h is actually 1, the limit of h approaching 0. Now, the next thing we need to look at is the graphical proof. Like I said, don't worry about writing this down, you'll get all this. So if you consider this a circle of radius r, and you know that this is x is between 0 and pi over 2. Alright? Now, just having a look, area of OAB, that triangle here, is actually less than the area of sector OAB, correct? By that bit there, that much there. Yeah? So using what you have learned last year, half r squared sine theta, or sine x, equals to half r squared x. Getting rid of those two, sine x is less than x, and therefore sine x divided x is less than 1. Alright? That is one thing. Think about that. Sine x over x is less than 1 because of the, you know that by rearranging the area of this and the area of this, you know that sine x over x is less than 1. Now, another way of looking at it, if you do a tangent at A, alright? Again, x radians is between 0 and pi. You can work out, you know that this is radius, and this is tangent at A. You can actually work out the area of sector OAB. OAB, that sector, is actually less than the area of the triangle OAC. Alright? So, again, we know that OAB is half r squared. Now, the triangle, the area is half OA times AC. OA times AC, half base times height, and therefore you know that's r, and that's r tangent of x. Alright? And here, again, we can eliminate half r squared. So therefore you know x is less than sine x over cos x. Tangent is sine x over cos x, correct? And therefore cos x is less than sine x over x. Alright? Those two things. Keep that in mind. Now, let's combine sine x over x less than 1 and cos x is less than sine x over x. Alright? See what I'm getting at. So I'm getting this point here, cos x is less than that. Combining that, and this is over there. Alright? So, sine x over x is less than 1, but it is greater than cos x. So as x approaches 0 from the positive side, you know cos x equals to 1. Alright? Now, The squeeze theorem or the sandwich theorem states that if fx is less than gx and less than hx for all numbers, and at some point x equals to k. Therefore, we have fk equals to hk, all right? Because they are, at some point, they are the same. Therefore, gk must also be equal to that. So since sine x over x is squeezed between cos x and 1, so therefore the limit of h approach, should be x approaching 0, sine x over x is 1. All right? So it's just theory that you need to know. So that is what you need to know. Limit of h approaching 0, sine x over x equals to 1. Then if you differentiate that, let's think about here. So we now know this is 1. All right? This bit here. Sine h over h is 1. So cos x times 1. How do we establish the limit of 1 minus cos h over h? All right? Again, use your class map. Evaluate that, please. And plot. Evaluate and plot. So you can see that the class map is telling me limit of 1 minus cos x over x is 0. All right, use your class map. Now, from there, if you plot it, this is what you get. Again, you know that x, when x is 0, that function doesn't exist, correct? Yeah? So that function is undefined at that point. But we're talking about getting closer and closer. What happens when you get closer and closer? That's a limit. So again, you can see that when x approaches from the negative side, approaching from here or approaching from there. All right? Either from here up or there down. You can see that as it gets smaller and smaller, the value becomes 0. So therefore, the limit of limit of x approach 0 for 1 minus cos x over x equals to 0. Which brings me back to that. All right? Or you want to do the trigonometric proof? I'll leave this to you to read. What I've done here is actually just change that. Multiply the top bit by 1 plus cos x, and so that I can change that to sine x, that's all. All right? And it becomes 0, and therefore, we know that cos x times 1, this is 1, and this is 0. So therefore, differentiating sine x, we get cos x. It's a long-winded way of telling you the first derivative of sine x is actually cos x. That's all. All right? That you must know.
So,
Yeah?
there would be a question in like exam about driving it, would there?
I don't think so.
They can ask it, but they never ask it.
They can ask you, but I have never seen any question like this.
Yeah.
All right? They can ask you about the limit or whatever, but
How many marks would a question like that be?
no idea. All right? So, doing cos x is the same by principle. Again, I'm not going to go through it step by step. I've established that. Therefore, you know that fx equals, the first derivative of cos x is minus sine x. That you need to know. Those two you definitely need to know, all right? Now, using that idea, can we actually derive using quotient rule to differentiate fx equals to tan x?
Yes.
So what is tangent x? What is tangent x?
Sine x over cos x.
Yeah, so if I've got fx, this one I want everyone to do, please. Let's try it. So here, F
I have no idea what
fx is actually sine x over cos x, correct? Yeah? So using your quotient rule, first derivative of x will be cos x squared, correct? Now, please, for quotient rule, you must always follow the fact that I have to differentiate the numerator first, and then take away the differentiation of denominator, all right? Differentiate sine x, I've got cos x, correct?
Where's your
And then multiply by cos x,
Huh? Where's your lost my pen?
take away. Now, differentiate cos x, that is minus sine x, correct? And then multiply by sine x.
Where's your Ken?
So therefore, you've got cos x, cos square x minus sine square x over cos square x. Now, from Pythagoras' theorem, you should know that
Doesn't make a
that's
difference.
plus, sorry, not minus. What is that? Cos square x plus sine square x?
1.
1. So is 1 over cos square x. Alright? Now, I am showing you
Calculator.
that sec square x, but you really don't have to know. That is for spec. This bit is for methods. So that is additional information, that's all.
Why does it?
Yeah, if you
For
value
spec, you
that,
need to know. For method, you
Is that
don't.
the same
if you
thing?
simplify it, it's the same
So
thing.
for any question that you do in the exam or
Sine square
test,
x over
if
cos
you have to
square x.
differentiate tan x,
Yeah.
One
for
is cos
methods,
squared
just
x
1 over
over
cos
squared
square x.
together.
Alright?
Same thing.
So this is a summary. And again, when we investigate the differential relation of the trigonometric function, all angle measures are in radians. Alright, I know there's a lot of theory in there, but like I say, you need to know this bit, and you will be able to apply that. I have got some exercises for you to do.